Hello, ladies and gentlemen. We're going to do 7.2b today. We're going to be talking about our volumes of solids of revolution. That's a lot of words. And we're going to be using the washer method and the known cross sections method. So we've really kind of talked about, our objectives already, and we've actually talked about the washer method already a little bit, but this is what's going to be our new information today. But I'm going to go back and talk about this washer method first. So we did talk about it in class in a few of the problems that you were doing. But if I have a donut, donuts, and I want to calculate the area of the donut, then the area of the donut is going to be the area of the whole minus the area of the whole. Alrighty? So that is a very important thing to think about when we are revolving our solids about an axis. Okay? Well, then if we want to make this look like calculus, then we're going to say that the volume of a donut, because donuts have volume, is going to be pi times the integral from A to B of the area of the whole, quantity squared, minus the area of the whole, quantity squared. And then, of course, we're going to put in the thickness of our donut, and we're going to get our dx. Well, to make it look even more official, we're going to call this pi integral A to B, capital R of x, quantity squared, little r of x, quantity squared. Get some nice parentheses in there. Oops, that guy's going to be a dx. So that's how we calculate the area of a revolved solid where the axis is not axis of rotation is not actually going through the individual object. All right, so I think the easiest way to do that is just to do a couple of examples, and our dog Ginger just decided to join us. We want to find the volume, Ginger, of the solid. As she leaves, we'll close the door because she likes to come in and bark, formed by revolving the region bounded by, I think I'm scribbling a little bit today, by the graph of y is equal to the square root of x and then our other one is y is equal to x squared and the x-axis. So if I graph my two little handy-dandy, and I'm going to continue with black just so I can add some color in a little bit. If I graph my two handy-dandy equations, if I graph y is equal to x squared, we know that it looks like this, okay? And then if I graph, so I'm going to call this y is equal to x squared, the square root function, it's going to look like this, y is equal to the square root of x, and then I'm going to add some color. All right, we can find this point of intersection between the two graphs. It's going to intersect at 1, and remember I can set these two equations equal to each other and solve. But I want to revolve this cute little fish-looking shape right here about the x-axis. So if I think about my area of the whole, and I'm going to use my red one, the area of the whole would be that. And so I'm going to write the area of the whole is going to be my radical x, quantity squared, and then my area of the whole is going to be this part down here. It's going to be what's underneath this curve, okay? And if I take the area all the way down to the x-axis and I subtract this area, let's try some green, just because we can get in all kinds of colors in there, then I'm going to get the area of the donut, okay? So if I fill in my other information, the area of the whole, I'm going to turn that light because it's kind of dark. Ooh, that's really bright now. Maybe we can make it a little bit less bright. So then the area of the whole was the area underneath the parabola, so then that was going to be x squared squared. And so then if I set up my integral for the volume is going to be pi, because we're still getting a circle, we're getting a donut with a hole, and it's going to be the integral from a to b, r of x squared minus r of x squared, and then I'm going to have my dx, right? So then if I fill in my information, I'm going to get pi. I'm integrating from 0 to 1 because those are the 2 points of intersection. The area of my hole, is radical x squared minus x to the fourth. I'm just going to go ahead and write that one already squared, and then dx. And then I would clean this up a little bit. This is pi integral from 0 to 1 of x minus x to the fourth dx. And again, I'm going to assume that you're brilliant, and so your volume is going to equal 3 pi over 10. Oops, you can't see the 10. So that's it for that one. So that's pretty handy. Ooh, my paper's turning blue again. That's always just weird. Okay? So then let's try another one. For our next example, we're going to have a manufacturer in USA. That's always a weird word to spell. Drills a hole, that's an A, hole through the center of a metal sphere, and our metal sphere is going to have a radius of 5 inches. Okay, the hole has a radius of 3 inches, and I want to know what is the volume of the resulting metal ring. And in my head, it doesn't really look like a ring, but it would be kind of like a metal ball with a hole through it. So if we have a sphere and it has a radius of 5, we assume that this is located at the origin. And let me see if I can turn that around, which means that the equation would be x squared plus y squared is 25, because remember it's the radius squared. I'm going to solve for y, so I'm going to get y is equal to the square root of 25 minus x squared. And then if I have a hole with a radius of 3, if we can visualize our sphere, the sphere is centered at the origin, so it's going to look something kind of like this. Again, don't criticize me too much on my drawing abilities. And so here's going to be the hole that goes through. It's lovely. It looks like an olive. It goes through this particular sphere, and then this radius right here is going to be 3, which means that line is y is equal to 3. Okay? And then that would give me the radius of the hole. All right, so if I'm going to calculate the volume of the revolved solid, remember that the radius of our circle is here, and then we have a hole going through it, but I need to find out where these two guys intersect. So I'm going to set my two equations equal to each other. So I'm going to have 25 minus x squared is equal to 3. I'm going to solve for x, so I'm going to square both sides, and I'm going to get 25 minus x squared is 9. A negative x squared is a negative 16, and then x is going to equal plus or minus 4. So even though it would appear that this would be integrated all the way out to 5, we're actually going to integrate from plus or minus 4. So this is going to be a negative 4, and then this is going to be a positive 4. And then if I write my equation as the area of the hole minus the area of the hole, then the volume is going to equal pi. We're integrating from a negative 4 to 4. The whole would be 25 minus x squared, quantity squared, there's my left parentheses, minus the whole, which is 3 squared, parentheses, dx. And then if you do all of that math, you would end up with your volume being 256 pi over 3. And if I'm skipping too many steps, you can talk to me about it in class, but I'll just simplify the radical a little bit, because remember, I think you're brilliant, so this is 25 minus x squared minus 9 dx. So this is just pi negative 4 to 4. 25 minus 9 is 16 minus x squared dx, and that is indeed a very easy integral to evaluate. All right, write my conclusion statement at the end of my work, and I'm going to get that my volume is equal to 256 pi over 3, and it would be the volume from a negative 4 to 4. All righty. So far, if we do a little bit of review about the things that we've talked about in this particular chapter. We have talked about the area between curves. And remember that this particular equation, it's just going to be the integral from a to b of f of x minus g of x, and then I would have dx, okay? I could also evaluate it from right to left, and I could evaluate it with my rectangle being a dy. So I could evaluate from c to d of f of y minus g of y dy. And it just depends on the orientation of the curves which particular method you would use. So then we started talking about the volumes of our rotated solids. And we talked about the disk method. And just to make sure that this is sticking in your head, so if I take, can I do that? If I take an image like that particular equation and I revolve it about the x-axis, okay, then I am going to have, and I'm going to draw the other side of it. So here's the other side, here's it revolved, makes kind of this kind of shape, and then I'm going to have a rectangle, right? Well, this particular rectangle is a washer, which is why we call it the washer method, and it's basically a circle that has some thickness. Again, I know I shouldn't quit my day job, but this is the thickness of the washer, which depends on whether you're rotating about the x or the y axis. So this is either delta x or delta y, depending on which axis you're rotating about. And then if I take this information right here and I do the top minus the bottom, that gives me the height of my object that I'm rotating, and the height is the radius. And so when we rotate the radius, it creates a circle. So this radius, remember the area of a circle is pi r squared. My radius is here, but my radius is also top minus the bottom. And because the axis of revolution is in the middle of the object, then it's just going to be this particular distance squared, okay? So then what we started talking about was the washer method. And we actually did some problems in the book before I showed you how to do it. But if I take the volume of a rotated solid using the washer method, basically it's just going to be the same equation. It's the area of the circle, but now the circle is going to have a hole in it. So it's the area of the hole minus the area of the hole, and then dx, okay? So that makes it pretty easy. So you just have to make sure that you're looking at your diagram and trying to decide what the area of the hole is, and then subtract the area of the inside, okay? And this can be top to bottom, it can be right to left. Remember, you always have to be careful to pay attention, am I using a dx or a dy? But what if the cross-section, so all of these have been a cross-section, what if our cross-section is not a circle? And this would be, what if my cross-section was a square, or what if my cross-section was a triangle, and then my triangle had some thickness, right? Or maybe my square had some thickness, and this was what's called the known cross-section. And you always want to look for those words when you're doing these problems, and that would differentiate this type of problem from the washer method or the disc method. So if I have a known cross-section, then my volume formula is going to be the integral from A to B. Notice there's no pi out front because it's no longer a circle. It is one of these other shapes, and it could be other things as well. It doesn't have to be a square or a rectangle, but it is the area of the cross-section times the thickness of the cross-section. This particular formula is used if the cross-section is perpendicular to the x-axis, and I can't draw pictures of this for you, so I'm really sorry. So you're going to have to look in the book to get a pretty picture because mine kind of suck. And then if I had this particular equation, that means that my cross-section would be perpendicular to the y-axis. And the cross-section method, when I have a known cross-section, also means that you need to remember your formulas for the areas of a square, a rectangle, a triangle. There is a special formula that I want you to remember for triangles because oftentimes what they'll tell you is that you have an equilateral triangle, and I'm going to call this angle A, angle B, and angle C. If it's an equilateral triangle, all three sides are equal, and there's a lovely formula from pre-calc that says that the area of the triangle is equal to 1/2 the length of one side times the length of another side times the sine of the included angle. And if you remember this formula, it saves you a ton of work trying to figure out what the height of the triangle is, and it cuts down the amount of trig you have to use. The caveat with this is that you have to be given, and I'll draw a clean triangle, you have to be given side, angle, side, and it only works in that particular situation. But I can find the sine of an angle using my special right triangles. I typically know the base of the triangle or the sides, and this is significantly easier. All right, so let's do an example, and we're going to have a triangular cross-section. Okay. All right, so in this one, and I'm going to kind of write the given down as we go. Triangular. And I'm going to attempt to draw a picture for you, but it's just don't get your hopes up too much. So this is going to be our y-axis. It's been rotated 90 degrees a little bit, or maybe 45 degrees. So this is y, this is x, and I know that on the y-axis I go from a -1 to 1, and on my x-axis I go to 2. So this is going to be the bottom of the triangle, and then this is going to be the height. So if you can visualize, this is my three-dimensional figure. This end, I guess you can't see jack, this end is smaller than this end, and I'm going to have a triangle right here that is perpendicular to the x-axis. And then I would have some depth to my triangle. So I'm going to draw it kind of like this. Ooh, it's just ugly. There's the depth of our triangle. So this is going to be the perpendicular cross-section to the x-axis. I'm going to tell you that f of x is equal to 1 minus x over 2. And I'm going to tell you that g of x is a -1 plus x over 2. Notice that these are simple little lines. And if I pull this diagram out and think about it, so this is going to be my y-axis. Okay, and so this is a 1, this is a -1, this is 1, this is 2, and this would be my perpendicular cross section. Okay, so to be able to get the base, and we often talk about that word when we're trying to do a known cross section, it's going to be the top curve minus the bottom curve. And in this particular case, that would be f of x, because this is our f of x and this is our g of x, right? I have a negative slope and a positive slope, right? Y-intercept, y-intercept. So it would be the top, 1 minus x over 2, minus the -1 plus x over 2. And when I clean that equation up, I'm going to get that my base is going to equal 2 minus x. Okay, so that's going to be my base. That's going to be this distance here. Okay, well then if I want to find the area of the cross section, okay? It's going to be that the area of the equilateral triangle, and I'm sorry, you were going to be told, so this is a given, this is an equilateral, which makes my life so much easier. So we're going to be told that it's an equilateral triangle. So the area is 1/2 side, side, sine of the included angle. Okay? So then this is going to be 1/2. My sides are the same. The base and the side are the same thing. So it's going to be my 2 minus x quantity squared times the sine of 60, because if it's an equilateral triangle, then the angles would be 60. So then this is 1/2, 2 minus x quantity squared. And if you go back and remember your 60, this is radical 3, 1, and 2, so the sine is radical 3 over 2. So my area formula becomes radical 3 over 4, and then 2 minus x quantity squared. So that's my area formula. I'm going from 0 to 2. This would have been given. We could have also figured out what the x-intercept is by setting our equation, the y equal to 0, and then solve. So then I'm going to do for my volume, the generic formula is a to b, a of x dx. Well, I'm going to integrate from 0 to 2. This was my area formula, so it's going to be radical 3 over 4, 2 minus x quantity squared, and then there's the thickness of my known cross-section. This little guy's a constant, so we pull him out front. So this is radical 3 over 4, the integral from 0 to 2 of 2 minus x quantity squared dx. You could integrate either using u substitution, or you could integrate by just expanding the binomial and integrating each individual term. When I do that math magic, I end up with 2 radical 3 over 3. If you leave it in its unrationalized form, it would be 2 over radical 3 would be the volume. Write your closing statement at the end. And we integrated from, where did we go from? 0 to 2. That was the volume. And then we're done. All right. So let's do, I have 2 more of these to do, just because the known cross-sections tend to be the hardest to visualize, I think, because I can't draw them to save my soul. So in our next example, we're going to have the base of a solid is a circle with a radius of 4 inches, and all cross sections perpendicular to the base are squares. All right. Well, if the base is a circle, then we assume that it's centered at the origin. And so I'm going to write and draw this kind of at the same time. So here's my lovely little circle. And the equation would be x squared plus y squared is equal to 16. We always have to solve this equation for y, so I'm going to solve and I'm going to get y is equal to the square root of 16 minus x squared. And so I know that this is a positive 4 and this is a negative 4, okay? Another thing to think about is I know that this image is symmetric, and I could technically integrate from 0 to 4 and double it, or I could integrate from a negative 4 to a positive 4, okay? So the next thing that I want to think about is the base of our cross sections, and it says that they are squares. Well, if you think about this, let me use a different color. This distance is y, and this distance is y, right? And so that means that the base of the square is going to be 2y, alrighty? So then the volume is going to be, which is perpendicular to the x-axis, is going to be the integral from a to b of a of x dx. But if my area is a square, then I know that a of x is going to be side squared or base squared, which is going to be 2y squared, which is 4y squared. So now I can rewrite my volume formula, and I'm integrating from a negative 4 to 4. So my volume is going to equal the integral from a negative 4 to 4, and again, it's no pi because my cross-section is not a, my cross-section isn't a circle or a disk, it is a square. My area formula is 4. My y is the square root of 16 minus x squared dx, okay? I'm going to bring that 4 out front, so it's 4 integral negative 4 to 4 of 16 minus x squared dx. Well, now it's a pretty simple integral to integrate. If I do this math, I get that my volume is equal to 341.333, and then I would write that it's the volume of the solid, and if I wanted to, I could go that I integrated from a negative 4 to 4. Now, we have been skipping doing this math by hand. Remember that on an FRQ, you are often asked to do this by hand, so you might want to make sure that you can do this by hand. All right, I have one last example for us, and we're going to do another equilateral triangle just because we can. So the base of a solid is a circle with a radius of 4 inches. They kind of like this poor little circle. All slices perpendicular to the x-axis, and I'm sorry I have not drawn this for you, but I can't. It would just be more confusing than if I actually attempted to. And we're going to know that they are equilateral triangles, so it's better off if we just don't even go there. So that if I draw the picture, it's going to be virtually the same picture that was up above. Here's my x and y axis. This is a negative 4 to 4. So it's the same basic problem. The only thing that's changed is how we calculate the area of the base. All right, so then here is my little slice, okay? And my slice is going to be a delta x. This distance is y, this distance is y. So my base is going to be 2y. Now it's possible in some of these images that I would have to do the top minus the bottom curve to get my base, and then I could use that base in my area calculations. But in this one, it's a fairly straightforward image. So if my bases are equilateral triangles, that means that my picture would look something like this. This would be 2y, and this would be 2y. So then the area is going to be 1/2 2y, 2y, sine of 60. So this is 4 divided by 2, which is going to be 2y squared. And then the sine of 60 is radical 3 over 2. 2's cancel, so it's radical 3y squared. So that's a pretty easy expression for your area. So your area is radical 3y squared. Oh yeah, and I know that x squared plus y squared is 16, so y is equal to 16 minus x squared. And then I'm going to eventually substitute that in for here. So my volume equation, again, I'm going to integrate from a negative 4 to 4. I'm going to pull the radical 3 out front. My area, y squared, so it's y squared dx. So this is radical 3, and I go from a negative 4 to 4. I'm going to bring in my y and square it, so I get 16 minus x squared, and then dx. And again, it's a super easy integral to evaluate, and when you do that math, and miracles happen because you're brilliant, you get 147.802, so my volume is equal to 802, and then whatever the units would happen to be. Alrighty, that's it for today. I will see you soon.